So in our last video, we had seen that the ratio between the rotor copper losses and the input to the rotor, that ratio is ns minus nr by ns, and which is nothing but slip. Okay, so so now what about this PM? Okay, so I want to know the relation between P2, PCR, and PM. Okay, so if P2 is 100% and this is slip percent, then obviously this is 1 minus slip percent. Okay? So, so that is what we are getting it. So if I want to know what is the ratio of P2 is to PCR is to PM, and that ratio is 100 is to S percent is to 1 minus S percent. So, or in terms of fractions, if I want to write it, so I'll get it is 1 is to S is to 1 minus S. Okay. So, what do we understand from this is if there is an induction motor, whatever, if 100% of power enters the rotor of the motor, so this is the air gap power, or this is the power coming from the stator. So there is a stator here. So from the stator, the power is entering into the rotor through the air gap, that is P2. So for every 100% power entering into the rotor, slip percent is lost here. Okay. So now, a couple of videos back, we had seen the torque slip characteristics. Okay. So the torque slip characteristics is something like this. So this is slip equal to 1, that means rotor is standstill, nr equal to 0, and this is slip equal to 0, that means nr equal to ns, rotor is rotating at the synchronous speed. And I mentioned that there is some operating point somewhere here. So typically this is the 0 slip, this is the ns equal to nr, and then this is the maximum slip corresponding to maximum, and then this part is the operating region of the induction motor. Now compare it with another characteristic. Let's say I have another characteristic, something like this. So let's call this one as B and the earlier one as A. So the characteristic A and B. Okay. Now this is the torque and this is the slip. So this is SA, and if I go to the, for the same amount of load torque TL, slip of A is different and slip of B is different, SB. So first of all, why these two characteristics are coming? So you can see here the maximum torque is same for both A and B, but B is having a higher starting torque. Okay. So what is the reason? The rotor resistance R2B is greater than R2A. Everything else remaining same. If the rotor resistance is more, then I get a higher starting torque. That's an advantage. But what is the disadvantage? The disadvantage is to meet the same torque demand of the load. Let's say torque demand of the load is 50 Newton meters. For the same 50 Newton meters, the first machine will have a smaller slip. Okay, let's say SA is 6%, whereas SB, let's say it is 10%. So in this case, while the machine B has the advantage of higher starting torque, but when it comes to the running conditions, there is a 10% losses, at least 10% losses. So the efficiency of the machine B will be less than 90%, because 10% anyway lost in the rotor. There will be more losses in the stator and the mechanical losses in the shaft. Okay. So whereas if I go for the first machine, efficiency of the first machine will be less than or equal to 94%, because 6% anyway is lost in the slip. So this is how you should interpret the slip. So the machine should be designed such that the slope here is very steep. So in that case, what happens? You can supply wide variety of torques with very less variation in the slip, and then very less amount of losses. So an efficient induction motor will have a steep curve here, which is starting like this. But what is the disadvantage? Whenever, as you have seen, whenever this part is steep, when it comes down, the starting torque will be lesser. Whereas if this part is slightly lesser steep, the starting torque might be more. Okay? In fact, if I use R2 equal to X2, then at the starting, when slip is 1, I'll reach the maximum torque, T max. Maximum starting torque you will get, that's a thing. But then when you are running under 50 hertz, 50 Newton meter load, so this time maybe even 30% may be the losses, which is highly undesirable. So anyway, so I hope you understood this, and this is a very important relation. The ratio of input to the rotor, to the copper losses in the rotor, to the output of the rotor, mechanical power developed, is 1 is to S is to 1 minus S. Based on this, we will be seeing some numerical example problems which are very, very important.